Okay, so welcome. Today I will show you how to design and test your own hardware Trojan. We'll do it exploiting a CPU backdoor for x86 architecture. Before I will start, a short disclaimer that the presented work disseminates the results of my spare time activities done solely using my own private resources. Therefore, the views and opinions expressed in this presentation are mine and mine only, and do not necessarily reflect the official policy and position of my employer. Examples presented within this work are only for demonstration purposes and does not necessarily reflect real-world products. So for those of you who just joined this presentation or which never read the description, what this talk will be about, in this talk we would like to discuss three questions which you see right now. How difficult it is to introduce a hardware Trojan or backdoor into a modern electronic equipment, how attacker can exploit such threats and extract your data, and what are principles of work of such circuits. So if those questions are interesting to you, or you wanted always to start your adventure with hardware security, or you just like to refresh your knowledge with respect to hardware threats, then this talk is for you. I assume that majority of you never designed or had not so much experience with design of hardware. So therefore, I will introduce some basics, but I also hope that people which have experience will find this talk refreshing, will find some things which they never thought about. So the motivation behind hardware security is, I think, pretty obvious. First of all, the importance of it is confirmed by the fact that it's a very hot topic in media. There are many discussions. We've got 5G network controversies. Some companies were accused, and even the whole institution, of providing critical infrastructure which could have potential hardware threats. We've got vulnerabilities in x86 processors. For instance, Meltdown and Spectre from Intel. In October 2018, Bloomberg reported the hardware Trojan could reach almost 30 US companies, including Amazon and Apple, although never a specific Trojan design or chip was presented public. Recently, there was massive Intel IP data breach, which mentions backdoor. The context here is still unclear. So some speculate it's a security backdoor, the others speculate it's just some programming structure. But still, the fact that this notion is discussed with regard to Intel and leads to very strong discussions shows that the topic is important. And also in research, in 2018, if you look on Google Scholar for hardware Trojan design, you will get 6,680 results, and this includes patents. In 2019, we have 7,160, and until September, so until yesterday, we have 6,050 already, which, so I think the trend is clear. It's constantly increasing. There's more and more money and resources which are directed towards hardware the security and countermeasures. But there is still no smoking gun evidence. So there is still no direct evidence of such threat. We had some stories where there was a cryptographic equipment sold, which could be classified as a backdoor or Trojan. However, there is no CPU backdoor, for instance, which can be publicly analyzed and confirmed, showing that this was basically this was the malware or malicious part of the hardware. Why it is like this? There are many reasons. It must not necessarily, maybe there are no real hardware Trojans, but we must also account for the fact that hardware products are closed source and reverse is very expensive and sometimes maybe impossible. There is, you can find many talks about reverse engineering of integrated circuits. There was also my talk on confidence about this topic. So that's the one reason. And the second, selected errors could be used as an attack vector, but still treated as bugs. So this is a notion which will repeat throughout this talk, that hardware is extensively tested and frequently comes the question if a malicious manufacturer finds a bug or vulnerability and will not patch it, is it already a CPU backdoor or still a bug? But many asks if CPU backdoor or hardware trojans are conspiracy theory. So once again, there is no very direct evidence of application real products. However, everyone can check if this threat is real and check the fact if it's practically feasible. So that's exactly what I will do in this talk for you. I will focus on practical example. So we all know that we can emulate running processor. And a very good example of such emulator, open source emulator, I think the most popular is Camel, which, this is a description from Wikipedia, emulates the machine's processor through dynamic binary translation and provides a set of different hardware models for the machine. So we can, with Camel, we can emulate many different processors with different ease architectures, Spark, ARM, x86. So if we can emulate running processor, maybe we can also emulate the CPU with backdoor and write an exploit for it on regular operating system like Linux. And this will be a goal of today's presentation. So we are limited in time, but I wanted to show you on a very simple example what's the logic behind such a hardware threat, how it can be exploited, and what attacker would like to achieve. So in order to do this, so to emulate regular x86 processor with a backdoor, we'll use Camel because it's very popular emulator, and we'll use also a Linux kernel. I use Buildroot with kernel version 4.15, but you can easily apply both on whatever setup you will have. The idea is that I would like to give everyone a possibility to repeat the experiment. Why x86? There is no particular reason. Maybe the one that many of us were or will be in the future exposed to this instruction set architecture have seen assembler, which is maybe not the easiest one or most elegant one, but still very popular. And I think it's very easy to comprehend what will happen. So modification available on my GitHub. If you would like to repeat the experiments, you are welcome. Just download it and try on your own setups. So this talk will be structured as follows. I will firstly revise for you security mechanisms in modern processors. So ring protection and memory management are main topics. Then we'll together design a CPU backdoor, and our design will be confirmed by proof of concept implementation using Camel x86 CPU emulator. And then we'll design also an exploit to leverage the OS protection mechanism for modern Linux kernels. After this, I will show you live demo. So you will see the backdoor and exploit in action, and I will conclude this talk. So there is this assumption, which forms the basis of a security of almost all modern systems, is that the processor is operating according to a strict specification, known set of predefined rules. So the set of predefined rules, the most commonly applied set of predefined rules, there were others before, but right now we are using usual hierarchical protection domains called protection rings, which were introduced already in the 70s for Multics. This is a Unix predecessor, so it's very old. According to this, your processor, independently if you are root user or regular user, independently of your privileges, processor itself runs at least two modes of operation, hypervisor and user. In hypervisor mode, kernel of your operating system has access to all commands and the whole address space. In user mode, only a subset of commands is available, and transition can happen only according to the predefined set of rules. So if we apply it to x86, x86 is using this theoretical model and apply it as follows. We have usually 4 different privilege rings. They are numbered from 0, which is the most privileged kernel mode, to 3, which is least privileged user. There are two intermediate levels which were used before and probably will be used also in the future, but if they are used, their usage is not frequent, and they are used for drivers and some virtualization activities. So processor must store somewhere information about the current mode of its operation, whether it be kernel mode or user mode. So it's stored in a register in the processor, and this value is called current privilege level, or CPL. And there is a very strong restriction who and when can change it. So you cannot just write to this register and change on yourself CPL value. It's done for you in hardware whenever certain actions are conducted in your system. I will be talking about those actions in a sec. And then the main resources which are protected are memory, peripherals, which are usually also memory mapped, and the ability to execute certain machine instructions. Although this was popular in the past, right now only few such instructions in x86 exist. And let us see how it works on an example of memory management in x86. This is how access to the physical memory is happening. This is obviously simplified view, but you have your own assembly instructions. From assembly instructions, you're getting logical address, which is passed to segmentation unit, which is getting linear address for you. Then you may have, but it's not a must. You may switch off paging, and at the end, you have physical address, which refers to your RAM modules. So in a real mode where there is no protection active, you have segment registers. We have 6 segment registers. There's a code segment, data segment, stack segment, and free registers, which you can use freely. And you translate your addresses in your segmentation unit very simply. Your assembly instruction deferred memory address offset. And from code selector register or data selector, you're using the base address, and you get your linear physical address. If we have a protected mode, then your code segment register does not necessarily, it doesn't have a raw number, but it contains index into a table of segment descriptors. And segment descriptor is providing you a base address. Plus, it has also a CPL value. It stores also a current CPL value of your processor. So segmentation protection mode boils down to what you see right now on the screen. Whenever you're trying to get some data segment, for instance, some memory location, you're comparing the maximum of your CPL and requested privilege level of your data which you are requested or instruction with descriptor privilege level. Its maximum, this maximum is simply because if you're in a kernel mode, you would also like to get access to the data segments from users with lower privileges. And as you remember, you can the higher number signifies lower privilege level. So if this if is true, then you can access the data, and if it's false, then you have protection exception. And then the last thing to revise is how to switch the mode. So when to switch, when the CPL level is switched, there are 3 main events when it happens. It's either a fault, it can be a page fault or some other exception. It can be interrupt, a keyboard interrupt or input-output finishing, or a trap system call. So you're running, you're executing your process, then you have interrupt, there is a trap of this interrupt, and the CPL is changed. There is a code from the interrupt descriptor table which will be executed. Then you're going back from interrupt routine, and you're switching once again your CPL in hardware, and you're executing your process. So after revision, we may start designing our CPU backdoor. So before we'll do it, we would like to firstly establish the goals of our actions. So our idea is as simple as possible. We would like to increase privileges of currently running process. So we are logged in as a regular user and we would like to be root. This is the classic approach. I don't have to explain you what you can do when you are root, when you did it. But this is an approach which was used in many other exploits targeting kernel. And so how to do it? We would like to find a place in memory where the information about the current process is stored, so process structure, and we would like to modify the data to override them and to be a root. The challenge is that if we try to access kernel memory with this part, with this structure, exactly what will happen will trigger this memory protection, and we'll get a protection error on the screen, and in our system will stop us. So the solution would be our backdoor in CPU, which should switch between the modes. So it will only switch for us in this example CPL, and all other malicious activities will be done in software. So for instance, overriding the privileges of currently running process. But this is the most likely way in which hardware threat will be exploited. It's a hardware software approach where some parts of the attack are done in hardware and the majority will be still done in software. So after establishing the goals of our attack, we can start to design our circuit. So just as a revision, hardware trojan or backdoor would be a function of a hardware component hidden from the user, which can add, remove, or modify the functionality of hardware component and therefore reduce its reliability or create a potential threat. So this function of hardware is constructed from two major components. It's a payload, so this is a modification of a circuit, and a trigger, which will be a signal activating the payload. So in case of our CPU backdoor design as a payload, we defined already what we would like to do. We would like to change the status of a CPL. The trigger must be visible to the user from the user space. So the majority of processors are governed by instruction set architecture, by assembly commands. Therefore, we'll use as a trigger, obviously, assembler command, but we must assure that the trigger is not easy to detect. So we would like to enforce that activation happens only in certain processor state, and it's not, for instance, triggered randomly in our system. So the simplest trigger which one could use is to use some known or hidden instruction. For instance, there is a sulk instruction. I'm using it here after Loic Duflot, which work I can recommend to everyone who is interested in the CPU backdoor design. This instruction was available from the beginning of 8086 architecture, but only documented since Fencing Pro. Note that there are in many ISAs, so instruction set architecture, there are certain set of instructions which are still empty. They are left empty spaces. If you look also on the Intel manual, there are still empty spaces, instruction set architecture. Those are for instructions and hardware accelerators, which may be coming in the future. We are just reserving some ranges for them so that we can offer a backward compatibility of our products. And not only instruction, we need some instruction which will trigger at the end the Trojan, but maybe it would be good to put some other additional conditions. So to put processor in a predefined state, this could be specific values of the register. If a processor has some other sensor, for instance, temperature, we could use it as well. And then make some conditional statements. So we are not only running the instructions we selected, but also check the state of the whole process. So in camel, there is this a big switch case in translate.c, a file where actually the translation of the specific instruction happens. And this translation, here you have functions which are altering the state of the emulated processor. So you see here from the top to down, you have a case, then the hexadecimal value of a return instruction from the x86 ISA, and then the code which is altering the processor state. So In order to implement our backdoor, we'll just find the sulk instruction. What I did, I just commented the part of the sulk instructions which was doing what sulk is supposed to do, and I have added this part, which is actually a trojan. We are just depending on CPL, switching, altering between the kernel mode and user mode. This is just a quick and dirty proof of concept implementation. You could do it better. You could still leave the values, the real sulk code there. You could make some conditions, as I was talking about, but it should already give you an idea how complicated it is to introduce such Trojan. You have 6 code lines here, and it works. So that circuit implementation, circuit translation would be also very, very simple. But of course, you can use even more sophisticated triggers. So for instance, speculative execution or branch prediction. So if our processor supports branch prediction, then if you have some conditional statements, we can compute them simultaneously and later discard one of them and do the rollback, the one which was never used. So the question is, what if an attacker would be smart enough to just trigger Trojan during the speculative execution, during some speculation of certain specific code, by executing several instructions one after another, or introducing some state of the processor, and then rolling back to the original state. This is very interesting because we know from Spectre and Meltdown that speculative execution can be tricky from security point of view, can leave your caches with some values which were obtained during the speculation. So such Trojan activation can be very difficult to be found. So all in all, combination which you are using should be rare in order to make it hard to find, or very rare, so it's easy for you to explain that it's a vulnerability or bug. And then we can start designing our software exploit for Linux. So those are the goals of the software exploit. We'll firstly place the CPU in the desired state, then run our trigger, in this case sulk instruction. Then we'll inject code and run it in ring 0. And then preferably one should go back to ring 3 in order to leave the same system in a stable state. Because if you are in a ring 0, then whoever programmed the kernel modules knows that system calls do not work, and it's very easy to randomly crash a whole system. So in order to do this, we have to firstly find our kernel data in our GDT table to be able to load those segments where kernel keeps its data. So where to find them? Their placement depend actually on your distribution, or may depend on your distribution, because they are defined in code. And as you all know, probably the code is the best documentation. So reading the code here for you, you can find the GDT entry for kernel is 12 multiplied by 8, and it gives you 0x60, and then you can find data segment under 13, and also multiplied by 8 gives you 0x68. And then this is our main part, main function of our exploit. We are running our sulk instruction. It's 0xd6, if you recall, the state machine of our camel. Then we are loading our data segment. Then we are loading kernel code segment, and we are making long code to a function which will perform actual malicious activities for us. So in this case, probably majority of you have seen this part of the exploit in other exploits for kernel, which are targeting interrupts or syscalls. What we are doing basically, we know our own user and group ID, and we go with a pointer through whole kernel stack from base to the top to find a place in memory where the current process information probably is stored. In our case, it's a second attempt, because what we are doing is we are looking for a piece of memory holding multiple copies of the current user ID and group ID. And if we find such a piece of memory which we think is containing our process structure, we are overriding it. So, and in such a way we have root, and we can return, which is byte 0xcb from the long call to this kernel function. So the last question, where is kernel stack base and the bottom? Oh, we can find it out from documentation, but obviously it may be set differently. So standard setting for embedded kernel like like the one used in Buildroot is 0xc on zeros for the bottom and 0xf for the top. So now let me show you a live demo. So we have a script which will run for us our compiled image. There is nothing special about it. It's just a script which is running our camel with our image of compiled Buildroot. And of course, this camel has already introduced trojan inside. So I will run our camel. It will need a second to start. Then what we'll do, we'll log in as a regular user, as a guest. And we'll try to execute firstly our script, which is overriding the process structure, but without activated hardware backdoor. And what we'll do next is we'll run the same script with activated hardware backdoor, and we'll see what will happen. So I'm logging in as a guest. And then we can see that I'm a guest. We can also check the version of our kernel. It's for 4.15 actually. And we can right now run our kernel space hack without switch on Trojan. So what you see here is a general protection fault. It's an exception, which shows that our code in kernel space hack was trying to get a segment which was not allowed to him. So we get segmentation fault, and we are left with nothing. And now we'll run our CPU backdoor as I introduced it to you by activation the SALC instruction. And then if I will check who am I have a root. So my user ID is 0 and group ID is 0. And if I will check who am I, it will show me that I'm root. So this is that. So that's that easy. Oops, I have to switch the presentation. Once again. Okay, so let's show. Let us get back to the slide where we left. So as you may see, the usage of the CPU vector is the same as the usage of any software kernel exploit. It just, instead of finding a vulnerability in an interrupt handle or a syscall routine, you have this vulnerability there in your CPU backdoor, which is changing simply processor state. So everything what happens next, data extraction, modification, is the same as in case of any other exploit, because this is a frequent question. There's a frequent misconception that you will get your data also in hardware, that there is some magic connection. There must be some magic connection to your Ethernet port, which is allowing you to extract data easier. It must not necessarily be a case. It might just help to get the root easier, as I presented to you. So this method is cheaper and faster for the attacker because kernel security is getting better and better thanks to you guys. So there is lower number of new exploits targeting the modern kernelers. It's easier to find exploits in other things right now. And there is also this philosophical question, which I mentioned at the beginning, and which is very important for us. there is a big threat for attacker, obviously, because by introducing such a hardware threat, he's actually he can get a very high cost and severe PR consequences if this threat is discovered. So it's because you cannot modify or change your hardware component, at least it's very difficult after it's introduced to the market. So what you're doing, you're testing extensively your components. And once again, what if you find a specific bug which is not obvious during your test phase and you just leave it? And the question is whether it is already a CPU backdoor or still a bug. This is probably your interpretation of the customer, but it would be very difficult to prove that this was the case. So it can be a vulnerability as it can be of meltdown inspector because there is still no attack presented which was using them, but it's still difficult to assess. So to summarize the stock, what I wanted to show you is that hardware threats are technically possible. So it's not a conspiracy theory. You can make your own accident. You can make your own experiments. You can repeat my experiment, conduct your own experiments. You can do it in VHDL. It's possible. It's possible to bypass this security. You may think also about situation when you are not changing the CPL. I use this change of the CPL register because it's the easiest way. We are using existing mechanism, but you could create a hidden mechanism which is bypassing CPL at certain situations. And then you can see CPL during the debug, but it wouldn't be possible for you to see this hidden mechanism. So it's also not difficult to bypass the hardware security in modern processor. In this case, it's only one single register which you have to adjust. And you can't offer software protection. So once again, software security is based on an assumption that you know what is the set of rules according to which your processor is working. So as soon as you break this set of assumptions, this set of rules, as soon as you alter it, you can't offer software protection. As I showed to you, we had a properly functioning Linux kernel, which just because malfunction of hardware was not able to protect the user against our exploit. So therefore, in my opinion, discussion about hardware safety is highly relevant, especially in the context of safety critical and security critical infrastructure. This is, so for instance, the critical telecommunication infrastructure. Why? Because if you can't properly assess or validate the hardware, if you can't check what's inside of the hardware, then obviously there will be always dependency between you and provider. And you must also consider in a worst case scenario or paranoid scenario that he can use or switch off this infrastructure for you. So just to finish what to do, how to live with hardware threats, I would say, first of all, there is a need to build skill force in hardware domain. I'm talking about personal tools. For instance, there is not that many fuzzers. So even software fuzzers, which are allowing you to fuzz the whole ISA architecture to try every instruction with every possible operand. It's just a beginning of such tools, but there are many other research possibilities in this direction. There would be good also to have procedures which are allowing hardware evaluation of hardware projects. So maybe it can be legislation to make some parts of the products open source, critical parts. Also movement towards open source products would definitely make attacker lives more difficult. And finally, as always, heterogeneous environment. So you can look at our example, which we discussed today, and you can see that I used several constants which are built into the kernel at compilation time. For instance, the position of the kernel data segment and the GDT table base and top of the kernel stack. As soon as you change those values, this obviously harder and harder for attacker to find to find appropriate spots. Also, address memory randomization could help, but there are still attacks against this. But definitely making your environments more heterogeneous, building your own hardware products, even if you are putting them from multiple different integrated circuits from multiple different providers, can give you better security level. Okay, thank you very much for your attention. I hope you enjoyed this talk, and I will be happy to answer all your questions.